Hello, once again. Welcome to this lecture on non-homogeneous equations. So this is a continuation of the lecture we began with in the previous videos. We already looked at homogeneous equations and the existence and uniqueness theorems governing that. So here we want to look at an introduction to the non-homogeneous equation, and then the superposition principle, existence and uniqueness theorems for non-homogeneous equations, and then perhaps in the second video, I'm going to do a short one on the method of undetermined coefficients, okay, for solving non-homogeneous equations. There are two main approaches for solving non-homogeneous equations, which are undetermined coefficients and the method of variation of parameters. So if I don't cover the method of variation of parameters, I will leave it up to you to read it out. I'm sure you know it already. Okay, so we've seen this equation before. This is a general equation, second order constant coefficient non-homogeneous equation if f of t here is not equal to 0. And there are two main approaches to solving it. First of all, to solve this equation, solve the associated homogeneous equation. Equate this equals 0 and solve the homogeneous part of it. The solutions you get are often called the complementary solutions, or which are given by this, right? That's the general solution for the complementary or the homogeneous part of the equation, where C1 and C2 are constants, okay? Now, the solutions Y1 and Y2 to the homogeneous equation are linearly independent. Of course, that's what you need. We've explained that already. And they are often called a fundamental set of solutions to the homogeneous equation. Okay, so first of all, solve the associated homogeneous part of the equation. Once you've done that, then you look for a particular solution, just one solution of the homogeneous equation, a solution that satisfies 16, right? That satisfies the non-homogeneous equation. Once you have the homogeneous solutions or the complementary solution, which is YC, and then you have one particular solution, then you add them together, YP, add it to the complementary solution, and that gives you a general solution to the non-homogeneous equation. So this is the general approach to solving the non-homogeneous equation, okay? Good. So in a couple of slides, we'll show why this is actually a general solution. But before then, we'll look at the superposition principle. And it's particularly important because you can use it to show that this is a general solution to the non-homogeneous equation. So we'll look at the superposition principle after we've looked at some other, and then we'll look at some other theorems as well. Okay, good. So let's look at the superposition principle or superposition theorem. It says that let Y1 here be a solution to the non-homogeneous equation given by this, and let Y2 be a solution to this second non-homogeneous equation. Then for any constant C1 and C2, the function, right, C1, Y1 plus C2, Y2 is a solution to the differential equation given by this, where the right-hand side here is basically a combination of the right-hand side of this first equation and the second equation, okay? In other words, if I have a non-homogeneous equation of this form, right, equation 18, to solve it, I could decide to split it into these two equations, all right? Write it as this and this, solve them individually, and then when you sum up, right, the solution multiplied by the constant C1 and C2, this then is a solution to the original equation that you are given. Okay, so in that case, it's very handy for solving equations of this form. Okay, so, well, to prove it, we just need to show that if Y1 and Y2 are actually the solutions to this equation and that equation, respectively, then of course, this guy here, we want to show that it satisfies equation 18. So all we do is substitute this into here and show that we get the right-hand side. Okay, so that's all the proof there is. Okay, so substituting this function into 18, the left-hand side is this, that is equal to A. In place of Y, I plug in all of this, right? So I have Y prime prime, so the second derivative of all of that, B, Y prime, B times this first derivative c times y. Y is the solution which is given by that. I can pull out the terms with the c1, and that gives me c1 multiplied by all of this plus c2 times all of this. Okay. Now note that y1 is a solution to, if you go back, y1 is a solution to this equation. So if I plug y1 in here, it should satisfy this. So this right-hand side with a y1 should be equal to f1 of t, and this with y2 has to be equal to f2, right? So that is what we have here. Since y1 satisfies the first equation, all of this guy here is f1, and that guy here is f2. And so we get the right-hand side of the equation. And so this is actually solution to that differential equation that we're trying to prove. Okay. All right. So as I mentioned earlier, as I mentioned earlier, one of the immediate implications of this superposition principle is that we can actually use it to show that equation 17, right? 17 is this solution, right? This solution here is actually this function here, I should say, is a solution to the non-homogeneous equation. In other words, it satisfies the non-homogeneous equation. That's equation 16, this guy. Okay, so that's one of the implications of that. And you can see that from this, right? If you have the non-homogeneous equation, you can write it as here, as I says, you can write if yp is a solution to equation 16, or in other words, you already have one solution, a particular solution to the non-homogeneous equation, and then you have a solution to the associated homogeneous part of it. Okay, so that is like these two equations where one of them is 0, the other one is f2. All right, so you have a solution to this part where this is 0, and that's the homogeneous part, and the solution to this part is yp. This theorem says that I can add the two solutions, right? I can add them and I get final solution. So that is what I'm trying to explain here. Okay. So in general, you can add them up and then you get a solution. So that's an implication of the superposition principle, one of the implications. Okay, so we really want to demonstrate, right? As I just said, we want to demonstrate that if we take the particular solution plus the solution to the complement, the particular solution to the complementary solution, you want to show that this actually satisfies the non-homogeneous equation given by this. So that's what we want to show now. We are showing it here because we need it in subsequent theorems. All right, so let's just prove it here. So I just plug this, all right? I just call this y and put it in here. Wherever I see y, I substitute all of this expression in it, okay? And see whether the right-hand side goes to f of t. And so the left-hand side is this, that is equal to, I have a times y prime prime will be the second derivative of all of this that is given by that, plus b times the expression, and then c times y, which is all of this. So take the second derivative of all of this, first derivative of this, and add it to this. I can pull out the yp terms, and that gives me this first expression here, okay? And then a times this second part, b times this second times, plus c times all these second terms. That is what this is saying. Note that yp is a particular solution to the non-homogeneous equation, which means that this guy here has to be equal to the right-hand side of the non-homogeneous equation, f of t. So this guy has to be f of t, okay? These three terms, I can expand them and then pull out the c1 and c2 terms, and that gives me c1 times ay1 prime prime plus by1 prime plus cy1 plus c2, and then the equation for y2. Note that y1 is a solution to the homogeneous equation, and then y2 is a solution to the associated homogeneous equation as well. Because they are solution to the homogeneous equation, this has to be equal to 0, right? The right-hand side of the homogeneous equation is 0. So this is 0, that is 0 as well. So I'm going to have f of t plus 0, which is just f of t. So this goes to show that this expression here, y, the particular solution plus the complementary solution, is actually a solution to the non-homogeneous equation. Okay, so that's what we've just shown here. Okay, good. So in the next theorem, we actually want to show that if this is actually a solution, where is it here? This y here, yp plus a complementary solution. If this is actually a solution to the non-homogeneous equation, we want to show that we can actually choose C1 and C2, all right, to satisfy some arbitrary initial conditions so that we get an existence and uniqueness theorem. Or we can actually show that the solution to an IVP exists and is unique because we can choose C1 and C2 to satisfy the initial conditions of the IVP. Okay, so we want to look at in the next theorem. Good. So here is a theorem, the existence and uniqueness theorem for non-homogeneous equations. Okay, so it says for any real constant ABC, T0, Y0, and Y1, want to suppose that YP here is a particular solution to the non-homogeneous equation. All right, that's equation 16, in an interval I containing T0. And that Y1 and Y2 are linearly independent solutions to the associated homogeneous equation, right? So 8 here is the associated homogeneous equation in I. Then there exists a unique solution in the interval to the initial value problem given by this, okay? And it is given by, in other words, the solution, that unique solution is given by this. We've seen this already for the appropriate choice of the constants C1 and C2. So first, this says that if I have a non-homogeneous initial value problem, okay, second order constant coefficient, a solution to that exists. The solution is unique, and the solution is given by this expression. All right, good. So what do we have to do to prove it? Well, first, we have to show that this is a solution. In other words, this satisfies this equation, which we have already done. Okay, that's what I'm explaining here. So that part we have already done. We have already shown that this expression here satisfies the non-homogeneous equation, so it is a solution. So there exists a solution, and it's given by this. Good. The next thing we need to show is that we can actually choose constant C1 and C2, right, to satisfy these initial conditions. Okay, and then finally, we want to prove that the solution that we get, this solution here, is actually a unique solution. Okay, so the first part we've done, there's a solution which satisfies this equation, and that solution is given by this. The next thing we want to do is that we want to show that we can actually choose this constant, C1 and C2, based on these initial conditions. Okay, so what we do is I plug in the initial conditions into the solution, right? YP at T0 plus, T0, if you plug T0 into the complementary solution, that should be equal to Y0, right? Here. Okay, and then differentiate it and plug in T0, and that should be equal to Y1. So that is what we have for the second equation. So we have two equations with two unknowns. So we solve them simultaneously for C1 and C2. So we have C1 to be given by this and C2 to be given by that. All right, you can go through the algebra if you want to, right? I should end up with these. Okay, so this C1 and C2 are fine as long as the denominator doesn't vanish, right? As long as this denominator, this expression here does not go to 0. But we know that that expression will not go to 0 because Y1 and Y2 are linearly independent solutions of the homogeneous equation. They don't go to 0, they don't vanish. Okay, remember the theorem on the Wronskian, right? If Y1 and Y2 are linearly independent, the Wronskian does not go to 0. And if the Wronskian does not go to 0, then Y1 and Y2 are linear independent. Okay, so this does not vanish. Because of that, we can conclude that we can actually choose C1 and C2 based on the initial conditions. C1 and C2 that satisfies the initial conditions given in the differential equation in the IVP. Okay, good. So we've done two aspects of the proof, right? We've shown that yes, the solution as it satisfies the equation. We've shown that we can actually choose C1 and C2 to satisfy these arbitrary initial conditions. And finally, we want to actually show that the solution, right, the solution to the IVP is unique. Well, for uniqueness, we want to show that if I have another solution apart from Y, right, which is YP plus a complementary solution, if I have another solution, these two solutions are the same. Or if you like, the difference between those two solutions has to be equal to 0 if I need to prove uniqueness. Okay, good. So to prove uniqueness, let's suppose that y underscore q here, yq of t, is another solution to the IBP20, the IBP we just looked at. And let the function z of t be the difference between our solution, right? And then this supposed new solution here. Okay, good. Now, if you plug this into the second order equation, we're going to get az prime prime plus bz prime plus cz. That should be equal to, right? Z here is the difference between the two solutions. So whatever I see z, I can plug in the difference. All right, then differentiate each of them and group the terms, and you're going to get these two expressions here. Well, note that y here is a solution, right? Y, if I go back, remember, we are calling this y. Y is yp plus this, okay? So that is y. Okay, so y satisfies the non-homogeneous equation, which means that this expression has to be equal to the right-hand side, which is f of t. So this guy is f of t. But we also said that yq is a solution to the non-homogeneous equation, all right? Which means that it satisfies it as well, which means this has to be equal to f of t as well. Okay, so we're going to have f of t minus f of t, and that should be equal to 0, which means that the function, all right, that governs the difference between the two solutions actually satisfies a homogeneous equation. Okay, so keep that in mind. Then secondly, we want to plug in the initial conditions to get initial conditions for z. Okay, so z at t naught will be y at t naught minus yq at t naught. Well, but y at t naught is y naught. Because yq is also a solution, right? Yq at t naught has to be y naught as well. So z at t naught is 0. And you can also show that z prime at t naught is also 0 because you have y1 minus y1, that is 0. Okay, so what we have here is a homogeneous equation, and the initial conditions are both zeros. All right, we've come across this before. So if you have the homogeneous equation and with 0 initial conditions, the only solution that satisfies that homogeneous equation is the identically 0 solution. Okay, so which means that the solution to this equation here with these initial conditions here is that z is identically 0. Well, if z is 0, if you go back here, if z is 0, it means that y is equal to y underscore q. And so the yq and the y are the same, all right? And so we have a unique solution. So proving that yq is actually equal to y, which is given by this. So we have shown that the solution to the second order non-homogeneous IDP has a solution, and the solution is unique. And we actually have a form for the solution. Okay, great. So we finish off with our final theorem here. This will be the last one, and then I'll end the video and then continue with the method of undetermined coefficients. Well, depending on the time. So the general solution, we want to show that the y that we just proved is a solution to the homogeneous equation is a general solution. What do we mean by that? So we couch this in a theorem that the general solution of the non-homogeneous equation 16, okay, can be written in the form y of t is equal to yp plus the complementary solution, where y1 and y2 are linearly independent solutions, or the fundamental set of solutions to the associated homogeneous equation. C1 and C2 are arbitrary constants, and yp is a particular solution to the non-homogeneous equation 16. So now we just want to, nail this and say that if you have the solution to the non-homogeneous equation is actually given by this, and this is a general solution. Good. Well, the first part of this theorem is to prove that this expression here is a solution, and we have shown that already, that this satisfies the non-homogeneous equation. So that part is done. We've shown that it's a solution. The second is to show that it is a general solution. What do we mean by a general solution? It means that if I have any other solution, call it YG, G for general, okay? If I have another, any solution YG, this solution YG here can actually be expressed in this form here, okay? The form given by Y or YS, okay? I just call all of this YS, okay? So, so given that this thing is a solution, all right? We know this is a solution. The form of the solution is given by this. we want to show that if I have a solution that is y of g, this y of g can always be expressed in this form. Well, how do you prove that? The way to prove that is that you pick constant C1 and C2, right? Such that the value of this, your solution, okay, YG here, at some point, say tau, is actually equal to the value of this expression at tau. And also you want to show that the derivative of YG at tau is also equal to the derivative of this expression here, YS at tau. Okay. And then by uniqueness, if YG and YS have the same value at tau and the same derivative of tau, by uniqueness, they have to be the same function. So that is the argument for uniqueness. And therefore, YS and YG has to be the same functions. Therefore, if I have any solution of the non-homogeneous equation, I can always express it in this form. And that shows that this form is a general solution to the non-homogeneous equation. Okay. So basically, that is it for the theory. All right, the theory governing non-homogeneous second order differential equations. Okay, so in order not to make the video too long, I'm going to pause, end this one here, and then when we come back, we'll actually breeze through the method of undetermined coefficients, show how you can use this to actually solve for a particular solution. We know how to solve for the homogeneous solutions, so we want to look at how you solve for the particular solution using the method of undetermined coefficients. Okay, so I'll come back in the next video to continue from here. I'll continue